All right, thanks, Jiangsu, and I'd like to thank the organizing committee and the program committee for the opportunity to speak. Can everyone hear me? All right, awesome. So I'm going to tell you about some joint work with Kevin Purbu. So let me start with this Schubert problem. This goes back to work of Schubert in the 1880s. And the problem is we're going to fix two non-negative integers, d and m, where d is less than or equal to m. And we're also going to fix several of these subspaces w sub I of c to the m of dimension m minus d. And the problem is to find all subspaces v of dimension d which intersect each wi non-trivially. So the idea here is that these wi's have codimension d, v has dimension d. So generically, when we intersect dimension d and codimension d subspace, we expect to get the origin. So what we want is we want the general behavior not to happen. We want v to be in special position with each of these wi's. And why do we have d times m minus d of these wi's? Well, that's because d times m minus d is the dimension of the space of all v's. So it's plausible that if we have dimension many conditions, we'll get a finite number of solutions. And it turns out we do get a finite number of solutions. So let's look at a concrete example. This is the classical example in Schubert calculus when d equals 2 and m equals 4. And in this case, our wi's and our v are two-dimensional subspaces of C4. But to make things more easy to visualize, we can projectivize. So if we take a hyperplane not passing through the origin and project everything to this hyperplane, then our two-dimensional subspaces of C4 will become lines in three-dimensional projective space. And so the problem is given 4 lines, where 4 is d times m minus d. So given 4 lines w sub I, we want to find all lines v which intersect our 4 given lines. And generically, there are always 2 solution lines over the complex numbers. And even in this simple case, these 2 solution lines are not easy to visualize geometrically, but we can visualize them in certain special cases, like this one depicted here, where W1 and W2 intersect each other and W3 and W4 intersect each other. So does anyone see at least one of the solution lines that intersects the 4 wi's? Yes, so the one passing through the 2 intersection points. And does anyone see the other line? Okay, yeah, I see some suggestive hand signals. So the each pair of lines will generate a plane, and generically 2 planes in 3 space will intersect in a line, and that is the other solution line. Okay? In general, there's a beautiful answer for the number of solutions v, at least when the wi's are generic, and that's this number f rectangle, the number of standard Young tableau of rectangular shape d by m minus d. So in this case, this number f rectangle is 2, indexing these 2 standard Young tableau. Okay, and just a technical comment. So I'm calling this a divisor Schubert problem. That's because each of these conditions is saying v lies in a Schubert divisor defined by w sub I. And that's just to say I'm not considering more general conditions than these. So in other words, I only have codimension 1 Schubert conditions here. Okay, now everything I've said so far is over the complex numbers, and it's often nice to work over the complex numbers because it's algebraically closed. But for many practical purposes or applications, we may be interested in solving the Schubert problem over the real numbers. And in general, it's like very difficult to prove anything in real Schubert calculus. But we're going to focus on this very particular problem posed by Fulton in the 80s for general enumerative problems, which is this question of how many solutions of real equations can be real. So for the Schubert problem, we could ask if we're allowed to fix these w sub i's to be real subspaces, how can we maximize the number of real solutions v? Can we get all of the solutions v to be real? It turns out the answer is yes, and a beautiful construction for this was proposed by the Shapira brothers in the early 90s, and their construction uses a special curve called the moment curve, gamma. It just sends a variable t to the first m powers of the variable t from 0, 1, 2 up to m minus 1, rescaled by these factorials. Okay, and we're going to take each of our w sub i's to be an osculating subspace to gamma. So an osculating subspace is a higher dimensional version of a tangent line. To get an osculating subspace, we just choose some number t and look at the point, the subspace spanned by gamma of t, the first derivative of gamma at t, and the second derivative of gamma at t, and so on until we get m minus d points to span an m minus d subspace. And the Shapiro-Shapiro conjecture is that if each of these wi's is an osculating subspace, then all of the solutions to the Schubert problem are real. Okay, so let's look at a picture. This is from a paper by Frank Sautile. And this is the same case as in the previous slide, d equals 2 and m equals 4. And again, we've projectivized, so we're looking at three-dimensional projective space. And this moment curve gamma here is in blue. It's what's called a twisted cubic. And here, the osculating subspaces are literally tangent lines. So we've fixed 4 tangent lines w sub I, which are these 4 lines in color here. And then we want to find all the solution lines in black which intersect all 4. So there's 2 black solution lines. One is here, and the other one is this line here. And this yellow thing is a surface containing both of the solution lines. So this conjecture is saying that in general, we can always see the solution lines in this real picture. A couple of comments. So this is not just a contrived Schubert problem. It actually arises naturally in several different contexts. It appeared in work of Eisenbud and Harris on linear series on algebraic curves. It appears in the theory of ODEs, and it appears in control theory. And especially in the last instance, it is interesting to have Schubert problems with all real solutions. Another comment is about this interesting work of Bergisser and Lorario on random Schubert calculus. And what they do is they take each of these wi's to be a random real subspace, and they look at the expected number of solutions, v, over the real numbers. And what they show is the expected number of real solutions is approximately the square root of the number of complex solutions. So in other words, the property of having all real solutions is very exceptional in the sense that it's far from the expected behavior. Sorry? Sorry, what much approach infinity? Yeah, so there's some error term which goes to 0 as, I think okay, I forget the exact result. Yeah. I don't want to misquote the result, but it is a, yeah. Okay. So that's the Shapiro conjecture, a bit of history. So it was posed by the Shapiro brothers in the early 90s, but Frank Sautile was the one who refined the conjecture and popularized it. Eryomenko and Gabrielov in the early 2000s proved the case of codimension or dimension 2. This case is particularly interesting because it can be rephrased in terms of rational functions and their critical points, though I won't explain how to do that. The conjecture was proved in full generality by Mukhin, Tarasov, and Varchenka a few years later, and used a remarkable connection with representation theory and mathematical physics, in particular, something called the beta ansatz. And a completely different proof was given by Levinson and Purbu a few years ago using topological arguments. Okay, so that's the Shapiro conjecture, which is actually a theorem and has been for a while now. But I want to talk about is a generalization due to Sautile from 20 years ago called the secant conjecture. And it's very similar, the setup is similar to the Shapiro conjecture. We still have this moment curve gamma. The difference is that before, these wi's were osculating subspaces to gamma, and now they're secant subspaces to gamma. So to get a secant subspace, what we just do is choose m minus d points along gamma and take the subspace spanned by those points. And we have an additional condition here, which is that if we take two different wi's and look at the two sets of points of secant c, we don't want those points to overlap along the moment curve. And the conjecture is that if we have this non-overlapping condition, then all the solutions to this Schubert problem are real, as before. And again, this is I'm only stating the form of the conjecture for these divisor Schubert problems, where we have codimension 1 conditions here. Okay, and let me just mention that the Shapiro-Shapiro conjecture is a limiting case of this one, because if we take a secant subspace and let the points of secant c along the moment curve approach each other in the limit, our secant subspace will become an oscillating subspace. Okay, so Eryomenko, Gabrielov, Shapiro, and Weinstein proved the case when each of these wi's has dimension 2. But besides that, there had not been much progress, and recently Kevin Prabhu and I proved this conjecture, which is what I want to tell you about today. So to start with, I'll tell you about yet another conjecture which implies this case of the secant conjecture. So to tell you about this conjecture, I need to define Pluecker coordinates. These are the same Pluecker coordinates we saw in a previous talk. So what we do is we take our d-dimensional subspace V of Cm, and we take a d by m matrix whose rows form a basis for V. So here I have a two-dimensional subspace of C4, and I have a matrix whose two rows form a basis. And the Pluecker coordinates are the d by d minors of this matrix. So in this example, they're the 2 by 2 subdeterminants. So for example, if I want to get the Pluecker coordinate delta indexed by 2, 4, I would look in column 2 and column 4 and take the determinant of that submatrix, which is 3. So that's why this Pluecker coordinate is 3. And it turns out that these coordinates do not depend on the choice of matrix up to simultaneous rescaling. So what's going on is that the set of all such V form an object called the Grassmannian, and these Pluecker coordinates endow this Grassmannian with the structure of a projective algebraic variety. Okay, so here's this positive version of the Shapiro-Shapiro conjecture, which is similar to this Shapiro-Shapiro conjecture we saw before. I've just highlighted the new parts in red. And just to clarify, so the original Shapiro-Shapiro conjecture was about osculating subspaces, and then the secant conjecture, we moved to secant subspaces. Now we're going back to oscillating subspaces. So each of these wi's is going to be an oscillating subspace to our moment curve gamma, but now we're assuming that the point t sub I of oscillation is positive for each wi. Then the conclusion is that not only are all the solutions V real, but all of their Pluecker coordinates are positive. So in other words, this solutions V all live in the totally positive Grassmannian. Okay, now if you're seeing this conjecture, okay, so maybe it's an elegant statement, but you might wonder, like, what does this conjecture really mean? The reason I was interested in this conjecture is because I showed its equivalent to an earlier conjecture of Eryomenko, which I won't state, but Eryomenko showed his conjecture in turn implies this case of the secant conjecture that we want to prove. And I won't explain how that implication works, but basically it's using some souped up version of the intermediate value theorem. So if we can prove this positivity conjecture, that will imply this case of the secant conjecture we want to prove, and that's what we prove. We prove the positivity conjecture. So now I want to try to explain how we proved this positivity conjecture. And our approach is that we want to view these points of oscillation, these t sub i's, as parameters, and we want to solve for this Pluecker coordinate, delta sub j of V, for a solution V in terms of the parameters. Now, this is, in general, this is kind of like a hopeless exercise. So these Pluecker coordinates are solutions of polynomial equations, and in general, we don't expect, given a system of polynomial equations, to be able to solve them exactly. Nevertheless, we are able to solve exactly for this Pluecker coordinate, not over the complex or real numbers, but over the group algebra of the symmetric group. And then, using this solution in the group algebra, we're able to get the information we need about the solutions over the complex and real numbers. So let me try to explain how this works. So our setup, again, is we have this special Schubert problem for oscillating subspaces. So each of these wi's oscillates gamma at a point t sub I, which I'm assuming is just some complex number. Later, I'll specialize the ti's to be positive real numbers. And again, we want to find all solution subspaces V that intersect each wi non-trivially. So what we do is we construct what we call universal Pluecker coordinates, beta sub j. So these are functions of the parameters t sub I, and they're indexed by d element subsets j of the integers 1 through n. So here you should think of j as indexing a Pluecker coordinate. And what we show is these linear operators pairwise commute. So basically they're simultaneously diagonalizable. And if we take a common eigenvector of these linear operators and replace each beta j by its eigenvalue, we obtain a set of complex numbers indexed by our sets j. And this set of complex numbers is precisely the set of Pluecker coordinates of a solution V to this Schubert problem. And moreover, we show that every solution V can be obtained uniquely in this way. Okay, so that's part one. Part two is what gives us the positivity conjecture. We also show that if the t sub i's are all positive, then our operators beta j are positive definite, meaning they have positive eigenvalues. And that tells us that the Pluecker coordinates delta sub j are always positive, which is what we wanted to prove. And I've kind of delayed the most important part of the theorem, which is what these operators beta j are defined to be. So we don't just show they exist. Actually, the fact they exist is some general fact in algebraic geometry called Stickelberger's theorem. But we actually have an explicit construction of them in the group algebra of this symmetric group. So I won't parse this whole definition, but I'll just point out that the definition involves some things we like to see in algebraic combinatorics. So we have this symmetric group. To our set J, we associate a partition lambda j in some standard way. And here we have this irreducible character, chi lambda, appearing. And so as defined, these beta j's are elements of the group algebra, and to view them as linear operators, we just let them act on the group algebra itself by left multiplication. Okay, so that's our main result. And just a comment about the proof. The most difficult part of the proof is showing that these operators, or these elements beta j, satisfy the Pluecker relations. The Pluecker relations are the defining relations in Pluecker coordinates, which cut out the Grassmannian. And to do that, we use a connection with something called the KP hierarchy. So the KP hierarchy is a system of PDEs that generalizes the KP equation, modeling shallow water waves. And using this theory, there's some way to translate the family of all Pluecker relations into an identity of symmetric functions. So basically, the most difficult part of the proof of this theorem is actually proving an identity of symmetric functions. All right, this is some stuff I'm interested in thinking about as future work, and thanks very much for your attention.
Okay, thank you. Are there any questions?
Thanks, this is a nice talk. So I'm wondering about the beta j's. Do they have other applications, or can you do other things with them too, like and replace the characters in there with imminence?
Yeah, it's very suggestive. We don't have any other applications or variations, but I'm hopeful that there is something.
Yeah, so it looks like the beta JSS matrices have size dimension of the Grassmann factorial, but don't you need degree by degree? Shouldn't the size of these Stickelberger matrices be the degree of the Grassmann?
I think the answer is yes. So really, what's going on is each of these solutions, V lives in some Schubert variety, which is indexed by some partition. And what you want to do to get those solutions is let these operators act on the irreducible representation indexed by that partition, which does have dimension, the correct dimension. Yeah.
Since you have you said it boils down to a symmetric function identity and it's coming from the KP hierarchy, can you rephrase the identity as a boson-fermion type identity?
I have to say I'm not familiar with that, so I'm not sure, but we can talk later.
More questions?
Can you say a bit more about, in your last slide, you mentioned that you wish to generalize, the question is about the second point and future direction. So can you say a bit more and how you think of generalizing Eisen-Schoenberg-Whitney's theorem?
Yeah, so in the case that d equals 1, our theorem is saying that if you have a polynomial with all real and negative roots, then it has positive coefficients, or that's what the positivity conjecture is saying. So obviously having all negative real roots is much stronger than having positive coefficients, and there's a theorem called the Eisen-Schoenberg-Whitney theorem that characterizes in terms of the coefficients when all the roots are negative and real. So I think it would be interesting to try to generalize those to Pluecker coordinates. So we should have much stronger, in the positivity conjecture, we should actually have much stronger conclusions than the Pluecker coordinates are positive.
Any other questions? Okay, then let's thank Stephen again.